Hello students, this is Niteen Mohod, and today through this video we are going to study two laws which are dealing with the electrical circuits. One is Kirchhoff's current law, which is also called as KCL in short, and Kirchhoff's voltage law, which is called as KVL. Talking about these laws, they are used to solve the electrical networks. They are also used to determine the equivalent resistance of the network of conductors and for finding the current flowing through various conductors. Kirchhoff's current law, that is KCL, is also called as point law. So far the statement of Kirchhoff's current law is concerned, it is stated as algebraic sum of all currents meeting at a point or junction or node in any electrical network is 0, or the total current leaving the junction equals to the total current entering the junction. And this we can say on the basis of since there is no accumulation of charge at the junction. So these are the statements which are very important so far the KCL or Kirchhoff's current law or point law is concerned. Through problem it will be clear. So problem on KCL, we are going to see here one diagram where we have shown the different currents. Some currents are flowing towards the node or towards the junction, while some currents are flowing out of the junction. This is the node where the number of branches are meeting, and this is the current going out, that is outgoing current, and these currents I1, I2 and I3, they are the incoming currents. According to Kirchhoff's current law, when we apply KCL to the circuit shown and find the equation, considering currents entering the junction to be positive, while the current leaving the junction as negative, equations for the given network using Kirchhoff's current law can be written as I1 plus I2 plus I3. Since all of the incoming currents we are taking them as positive, so I1 plus I2 plus I3 equals to outgoing currents I4 and I5, so is equal to I4 plus I5. On rearranging the equation, we can rewrite this equation as I1 plus I2 plus I3. On transferring these terms toward this side, so you will get minus I4 plus minus I5, means I1 plus I2 plus I3 plus minus I4 plus minus I5 equals to 0, which can be written in terms of the summation form as summation of all the currents, that is sum of all the currents meeting at the junction equals to 0. Moving on to Kirchhoff's voltage law, that is also called as KVL or mesh law, or it is also called as a loop law. The statement of the Kirchhoff's voltage law is in any closed path, which is also called as mesh or loop. So in any closed path in a network, the algebraic sum of product of currents and resistances in each of the conductors plus the algebraic sum of EMFs in that path is always equal to 0. This statement will be clear from the example, but before that we will see the equation for the Kirchhoff's voltage law. Generalized equation can be written as summation of IR, that is the product of current and resistances, plus summation of all EMFs is equal to 0. Before moving on to the example of Kirchhoff's voltage law or problem on Kirchhoff's voltage law, we must be acquainted with the signs of battery EMF. So we will see here, fall in voltage is treated as negative. As you can see from these diagrams, here this is the positive terminal of the battery and this is the negative terminal of the battery, and let the current direction is this, that is from positive to negative. This side means it is going from positive to negative this way. Now since it is going from positive to negative, there is a fall of voltage, that is, it is going from higher voltage to lower voltage. So that's why it's a fall in voltage, and it will be treated as minus voltage or minus E. So far the resistances are concerned, resistances have no polarities, but when the current flows through the resistance, the voltage drops across this resistance, and that voltage drop has got the polarity, like for example plus and minus, like this. See, let the current is flowing in the direction, same direction, that is from left to right. Under such circumstance, since it is going from higher voltage to lower voltage, you will get the resultant voltage negative, that is minus E. Exactly opposite to this, we will see the rise in voltage is treated as positive. From the diagram it will be clear. Here the direction of current remains the same, but the battery polarity has been reversed. So the current is going from negative to positive, means lower to higher voltage, and since it is going from lower to higher voltage, it is treated as plus E, or it is equivalent to plus E. Similarly, across the resistance, the voltage drop, if suppose the voltage drop is like this, that on this side the voltage polarity is plus and on this side it is negative, and the current direction is from left to right, means we are going from lower voltage side to higher voltage side, then it will be treated as positive voltage. The resultant positive voltage will be positive, that is plus E. Now, keeping these laws or these battery science conventions of the battery and this Kirchhoff's voltage law, we are going to solve one problem. So here this is the problem given. Here one loop is given, which is a closed loop, and within the loop the current is flowing in the direction like this, means clockwise. In this arm, current I1 is flowing, while here the current I2 is flowing, here the current I3 is flowing, and in this branch the current I4 is flowing. The problem is apply KVL, that is Kirchhoff's voltage law, to the circuit shown and find the equation. Now consider the direction of current flow as shown by the circular arrow, this arrow. This is the direction of the current which we will have to consider, and we are considering the loop. So now considering the sign conventions as rise in voltage as positive and fall in voltage as negative. Just now we have seen. For the closed loop A, B, C, D, A, that is A, B, C, D and A, means it's a closed loop. Applying KVL, we can write the equation like this. Now starting from this A, moving on to this B. So here we can say, now when the current flows like this, the voltage drop will be here positive and here it will be negative, means higher to lower, means fall in voltage, so negative. You will get the equivalent negative voltage. Now how the voltage will be calculated? The current flowing through the branch multiplied by the resistance in the branch. So I1 R1. So negative of I1 R1 will be the equation for this first branch. When you will reach to B, you are proceeding for the C. Means when we are going from B to C, we'll have to calculate the voltage which is existing in this particular branch. Now here the current direction is this. It means here the voltage drop is positive on this side and negative on this side. Okay, and our main direction of current which we are considering is this, means we are going in this direction. So when we are moving like this, so since we are going from positive is here and negative is here, and we are going from negative to positive, so this current I2 multiplied by R2, and it will be positive since we are going from lower to higher, so negative to positive. So plus I2 R2 you will get. Then we are continuing the same direction and reaching to C, and here we are going from positive plate to negative plate, which is falling of voltage, and that's why the voltage or EMF is taken as minus and minus E2. So you will get minus E2 here. Now we have started from A, we reached to B, we reached to C, and we got this much of equation. Now we are to move from C to D and D to A back. When we are moving from C to D, at that time the current direction which is flowing in the branch is from C to D, that is I3, and it is flowing through resistance R3. So when it is flowing through the R3, the voltage drop will be positive on this side and negative on this side. So it will be the fall of voltage, and therefore you will get naturally negative of I3 into R3. So negative I3 R3 you will get. So up to D it's okay. From D now we are moving to A. Now the current direction is this, which is same as that of the actual current direction which we are going to consider for the loop. When we are going from D to A, we are going from negative to positive, that is the rise in voltage. So plus E1 will be there. And so far the voltage drop across the resistor R4 is concerned, it will be I4 into R4. And since the current direction is this, it will from positive to negative. So fall in voltage, so it will be minus of I4 R4, that is equal to 0. So this way we have completed the equation for the complete loop. So this equation can be rewritten as, now here what we are doing, we are multiplying by minus sign throughout. So you will get I1 R1, here it will be minus I2 R2 plus I3 R3 plus I4 R4 is equal to, we are transferring these terms of E2 and E1 on the right hand side, so you will get E1 minus E2. Then moving on to the potential or voltage divider and current divider circuits. These are important so far the network theorem solving is concerned. In network theorems, we are going to study different theorems to solve the electrical circuit, and there these formulas will be very helpful. And considering that we are moving towards the formulas which are related to the voltage divider and current divider circuits. Now voltage divider circuit and the formulas associated with it we are going to see here. Here you can see a simple circuit which is having battery connected plus V, and in parallel with it, or sorry, it's a series circuit. So in series R1 and R2 resistors are there. Now here across R1 we are getting the voltage V1 and across R2 we are getting the voltage V2. Can we have some formula which will directly provide you the value of V1, or can we have the formula which will directly give you the voltage of V2? Yes. And for that only we are going to study these circuits. So here basically what we are going to see, we are going to first see that how much current is flowing in the loop. So V is the total voltage. So naturally the total voltage, you know the basic formula of basic electrical formula, that is Ohm's law. V is equal to I into R. So when we are going to calculate the current flowing in this loop, we will have to consider two things. One, the voltage in the loop, total voltage in the loop, and the total resistances in the loop. So here V divided by R1 plus R2. V divided by R1 plus R2 gives me what? V, that is voltage, divided by R1 plus R2, since they are in series, gives me the total current which will start from this positive terminal of the battery, which will flow through R1, which will flow through R2, and which will reach to this negative. Now the question is, what is the voltage which I will get across R1? Now for that, what you will require, the voltage drop across this resistance R1 can be calculated like the current flowing through this R1. Now just we have calculated the current which is flowing through this R1 and R2. This is common current which is flowing through R1 and R2 since it's a series circuit. So current calculated was V upon R1 plus R2. Now this is the current value, and this current value multiplied by the resistance across which we want the voltage. So V into R1 upon R1 plus R2. So V1 will be is equal to V into R1 upon R1 plus R2. Similarly, if I want to calculate the voltage drop across R2, again the same current formula, that is V upon R1 plus R2, that will be the total current flowing multiplied by R2. So V upon R1 plus R2 multiplied by R2. So that is V into bracket R2 upon R1 plus R2 will be the formula for voltage drop across the resistor R2. So this is how, by using the formulas directly, you can calculate the voltage drop across R1 or R2. So far the current divider circuit and the formulas associated with it are concerned. Here you can see the battery connected and the current is flowing like this up to this point. From this point, depending upon the value of the resistance R1 and R2, the current will flow Some current will flow through R1 and some current will flow through R2. This current will going to add at this point, and the total current will again flow out of this and will reach to negative. Here there is a formula for the current flowing through one parallel branch. Here we are considering I1 is the current flowing through this R1 and I2 is the current which is flowing through R2. And we are finding the formula directly for the total current flowing through resistor R1. So what is the formula, how it is written? There is one trick. Now if you want the formula flowing through R1, first take the total current flowing in the parallel combination. So total current flowing is I. So you are taking I. Then into bracket, you are going to take that resistance value through which we don't want the current flowing. Actually, we are requiring the current flowing through R1. We don't want the current flowing through R2. So therefore, this R2 you will have to take in numerator divided by R1 plus R2, the combination of or the addition of these two resistances. The same case is for I2. Now, if I want to calculate the resistance value of the current I2, and if I want to write the formula for current I2, so it will be is equal to total current I into bracket R1 divided by R1 plus R2. So these are the very important formulas. So for the voltage divider networks and current divider networks, and the current flowing through them and the voltage dropping across the different resistors are concerned. I hope the idea of Kirchhoff's current law, Kirchhoff's voltage law, and the formulas associated with, along with the sign convention, is clear to you. Thank you.